So, as I already explained our strategy, so we want to make each step. So from here we have H0, then we can delete some, and then we can obtain H1, and then we want to repeat. So we want to encapsulate this one step into the following lemma. So this lemma describes what happens in one step, and then later we will apply this lemma repeatedly to prove the Pippinger theorem. Assume again capital D and delta 0 is, capital D is large and delta 0 is small compared to these constant. So let's say there are capital K and small k. So formally again, we are given these four numbers, and there exists certain threshold, and as long as these two numbers are below that threshold, the following statement hold. Let H be a K uniform hypergraph satisfying the following. So for our convenience, actually we will, again, this will be almost regular with a small codegree, but we will divide this almost regularity condition into two. So for all vertices, but at most delta 0 n of them. So except a small number of vertices, all the other vertices has degree which is correct. But even the vertices with incorrect degree cannot have a too large degree. So this is actually weaker than almost regularity condition that we had in the Pippinger theorem. And again, the codegree is small. So we have this. Then this H has a set M prime of edges with the following property. Where V prime is we delete all the vertices inside of this edges inside of this collection, and let's say H prime is the induced hypergraph which is induced by this V prime. So this means that it has a vertex of V prime, and then all the edges of H which completely lies inside of V prime are the edge set of H is V prime. So what this have is, first, size of this M prime is almost alpha n over k, but C here, all the error term was measured by delta 0, which is much smaller than delta 1, but now in the result the error term gets less good. So regularity, in each step, regularity or the small codegree might get a bit worse and worse. But we want to make sure that it doesn't get too worse, so that we can still keep it into a good range. So here in this statement, we can actually choose delta 1. And this B prime also has this many vertices, and for vertices x inside of B prime, but at most delta 1 B prime of them has degree in H prime almost, close to t times e to the negative alpha k minus 1. So again, if we write this is a number between 1 minus epsilon and 1 plus epsilon. So if I write A is this times B, then we have this. So that's what it means here. So this is actually two inequality. Anyway, so what it means is exactly, what we wanted to do in this one step. If the initial one was very close to regular and small codegree, then you can actually choose some set of edges. And then once you, the set of edges has a correct size. And then once you deleted it, the number of vertices is correct. And then the remaining vertices induces a graph, which is, again, almost regular. And codegree one is easy because this is an upper bound of the codegree of this H prime. So we don't have to really care too much about the codegree. But this shows, this one repetition can be done. And first we assume this lemma and then see how it implies the Pippinger theorem. So again, let's take the statement here. So proof. So we first choose alpha which is much smaller than 1 over k, small k, and 1 over large k, 1. So, okay. So let's do this way. So, here the statement is for given epsilon and 1 over k. We should be able to find these which satisfy this, right? So these are given. And we choose some large number 1 over k as we want. And for given those, we will choose this alpha. So this relationship, so there are some implicit relationship that we will later use. But we will not really specify this. But if you actually follow the proof, then you can actually figure out which relation you actually need it here. And you can actually explicitly write it down. So as long as that relation is satisfied, then the later proof will work. But for now, we just specify that this alpha actually depends on these three things. And now we fix alpha, which is, again, never 0. And let t be an integer, which satisfies e to the minus alpha t is smaller than alpha. So you can simply write the 1 over t is smaller and smaller alpha. So given alpha, you also choose t so that the t is, much bigger compared to alpha. But the actual relationship we will use is this. But instead of this, we can, it's also okay to write in this way. And now we have chosen that. And now we choose delta 0, delta 1, delta t, say delta t plus 3, and D be a large, TB numbers, so that the following holds. So we have 1 over D delta 0 this. So formally, for this given 3, there is some relationship, there is some function, which, in the proof, we can actually find, explicitly find the function f so that the alpha is smaller than that. But among smaller alpha, we fix 1. And now, given this, we fix t as a function of alpha, which we will not specify. And fix this, and we fix another number, which is much smaller, which, again, there is this relationship, which we didn't specify. And then from here, next one, next one, next one. So this step is finitely many, so we can actually specify all the relationship here. And in fact, this relationship between the two consecutive delta will be the relationship which we get from this lemma. So these two deltas are consecutive one. So if we have a hypergraph with this many, with this much accurate, almost regular one, then you can obtain a next one whose almost regularity is roughly this measured by this. It's slightly worse. That's what this lemma says. So here we choose this because initially when we have a hypergraph with almost regular, and almost regularity is so strong, which is measured by delta 0, and then we will apply the previous lemma once. We can do that because this, two numbers are satisfying certain relation, which makes sure that this lemma can be applied. So we apply once, then error term becomes worse, and error term becomes worse, error term becomes worse, error term becomes worse. But at the final step, still error term is small enough compared to, say, epsilon. So later we can actually show that we can find the epsilon perfect, almost perfect hypergraph matching, which covers everything but epsilon fraction. So we choose these number. So now with that, now we start our proof. So let H0 be H, and let Di be D times e to the minus alpha k minus 1 I. So for example, D0 is D, and Ni be N times e to the minus alpha I. Again, N0 is N. So assume we have a Hi which is satisfying the following condition. Say Hi-1, that all x in this Hi, but at most delta I and I vertices has degree 1 plus minus delta I times Di. Hi2 is its maximum degree is almost this large K times Ti. H3 is that its codegree is almost delta I Di. So assume this holds. For example, H0 satisfies this because from this condition, So here, I didn't specify this. Delta and delta 0 are same. So what's this? We have to show that for given this, there exists a choice of that which satisfies this. So that's the statement. And what we did, for given this, we found this, and which satisfies certain relation. We found this, we found this, we found this, we found this, and we finally found this. So this comes from here, because all the middle one are just function of these three. So this comes from here, and this large K is just some number we also have chosen, coming from these two. So essentially these two determine this. So, and we assume that with these numbers, this hold, that implies this H0, 1, 2, 3. So initially H0 satisfies this, and now we apply the previous lemma with delta I and delta I plus 1 playing the roles of delta 0 and delta 1 in the lemma to obtain a K-graph, hypergraph Hi plus 1 which satisfies Hi plus 1, 1, and Hi plus 1, 2, Hi plus 1, 3. So that because this lemma says that what? So lemma here says this, and give me a moment. Let's add one more condition here, which I see. Let's say this Ki, and then Ki is nothing but the e to the alpha k minus 1 I times large K. Okay. Because initially we have assumed that then this Hi condition and Hi plus 1 dash 2 condition are actually, this is natural. So we apply the previous theorem. Then what do we know? We get a new graph which satisfy this condition and as well as this. First, because of this condition, here we automatically have this satisfied with I plus 1. So this holds. And the other also two holds because of this K gets a bit larger. And because alpha is already here, and then whatever it happens in, here, this delta is still smaller than, 1 over this K, 1 over this Ki. Because even if this Ki gets a bit bigger, but the relationship is still, a function from alpha and K. So when we choose these, we make sure that whatever we do with K and alpha and T, because here what we will do is we will obtain T times. We will obtain until we get HT. And each time this K is getting larger by alpha. So it's getting larger each time by this number, which depends on alpha, and how many times we will apply it, T times. So we will get some large number, KT here. but we have to make sure that these are all much smaller than that. So we can actually apply this lemma. Even if this is large, these are still small. So this relationship here required in lemma still satisfied. Anyway, so this comes, this immediately implies this. And here, it's also okay because the codegree of smaller graph here is again bounded by codegree of the original graph. But now delta gets larger and then d gets smaller. So di gets smaller, but the delta gets larger. And we make sure that this relationship between them, they are, the difference between these two in terms of multiplication is bigger than that. So this also satisfies. And not only that, but it produces, and we also obtain a set m prime I plus 1 of size, let's say m prime I. M prime I has size 1 plus minus delta I plus 1, which is coming from here. Alpha n I over k, covering, we have the second condition. Because of this, so once we delete all the vertices in here, then remaining one has this many edges, vertices. Then it covers initially we have this many vertices. No, sorry. So give me a moment. Let me add one. So we add one more condition that the number of vertices in Hi is 1 plus minus delta I times Ni. Then we obtain this H of size this. And this B prime, which is vertex set of Hi minus union of all the edges in M prime I, has size from this lemma, it has this size. This has 1 plus minus delta I plus 1. Give me a moment. Yeah. So okay. It's slightly getting more complicated, but okay. Let's do this. Okay. Indeed, the gap this here is, how we have chosen. so that this is, so we make sure that this relationship is our choice, so that if we apply the lemma with these two consecutive one, the lemma holds. Not only that, the lemma also holds with these two constant. So if you apply the lemma with this on the condition here, then we can not only get the delta I here, then we can actually get the delta I plus 1 here. Not only delta I plus 1, but you can actually get the, delta I plus 1 over 10 is also possible. Yep. Then here you get this is slightly better than delta I plus 1 over 10. So this is what we have. And what's Ni? Ni was this. And here you apply e to the minus alpha again. And let me write it this way. And previously it's this. So if you apply the lemma, then the last condition, second to the last condition, M2 implies this. And then what's this number? This number is 1 plus minus delta, I plus 1, 10 times, what's this? This comes from here, it's 1 plus minus delta I, and I, times e to the minus alpha. And once you multiply e to the minus alpha, this Ni becomes Ni plus 1. Ni plus 1. And then here, you know that this delta I is much smaller. So this is at most 1 plus delta I over 10 plus delta I times delta I plus 1 over 10 times Ni plus 1. So this is smaller than delta I. So this is 1 plus minus delta I plus 1 times Ni plus 1. So it satisfies Hi plus 1, 4. And moreover, we read Mi. So recall that this M prime I is not a matching, it's just collection of edges. We want to take a matching. This be the collection of edges in M prime I, which does not be the, be a maximum collection of edges which does not intersect with any other edges in M prime I. Then what do we have? In Hi, the number of vertices in Hi, you subtract this V prime. Then this is exactly the number of vertices covered by M prime. And this is actually all the edges in, let's write it this way to not confuse with the number of edges. So this is collection of edges. All the edges in Mi occupies k vertices. And then all the remaining one, because this is maximum collection, they occupy at most k plus 1 vertices. Then this is an upper bound. And what's this? This is, from here, you get, the previous one has size 1 plus minus delta I, ni, and then later one has 1 plus minus delta I plus 1, ni plus 1. And which is this is ni times e to the minus alpha. So this left-hand side is nothing but 1 minus e to the minus alpha times ni. It's a lower bound, so we take the lowest one. Then 1 minus 2 delta I plus 1. So this is lower bound. And actually, so this has this is smaller than, so 1 minus e to the minus alpha is smaller than alpha. No, not smaller than alpha. Let's just write in this way. And this upper bound part, so this part is what? So we know that m prime I has this size. So this is k times mi plus k minus 1 times the what up as an upper bound 1 plus delta I plus 1 times alpha ni over k minus mi, which gives us mi plus k over k minus 1 times 1 plus delta I plus 1 times alpha ni over k. We just move this to the other side. Then what do you get? That you get roughly 1 over ni over k. Give me a moment. K is not here. So you can actually write this 1 over k Give me a moment. Let's write it this way. So this part has a lower bound 1 minus alpha square. Okay. Ni. So this part is 1 minus 2 delta I plus 1 alpha minus alpha square ni. This is now equation we have. You move this part here, then that's k over alpha minus alpha square ni. Okay, this might be better. Okay, we have this lower bound. So sorry for the, sorry that I was a bit confused on the computation, but the point is that because we know that this M is a collection of edges, and we know how much it must, how much vertices it must cover. If all the edges are disjoint, you cover the maximum number of vertices. But you already know that it covers near maximum number of vertices. That means most of the edges must be already disjoint, except the small number. So you can actually compute this. So this is the computation. So it shows that MI has to cover at least this much, edges. It has at least this much edges, and MI is a matching. So you do this procedure T times. You get H1, H0, H1, H2, and so on. And you get this matching, then H0, H1, HT is a matching. And how many number of edges in here is at least summation of 0, I equal 1 to T. And you apply this. Let's just say this is, at least this number times alpha over k minus alpha square ni. Then this is 1 minus delta I plus 2 times alpha ni over k minus alpha square ni. And how big it is? You know what ni is. So I is 0t 1 minus delta 2 k over alpha n minus alpha square n times e to the minus alpha I. And as this number is much smaller than, say, alpha, so you can simply replace this. It's a lower bound. You have this. Then what's this part? This is 1 minus e to the minus t alpha over 1 minus e over e to the negative alpha. And what do we know? This is much smaller than alpha. So we make sure that this is smaller than alpha. So this is 1 minus alpha, alpha n over k minus alpha square n. And this part is lower bound by this. Then this is 1 minus alpha square n over k minus alpha n. And we know that alpha is much smaller than epsilon or 1 over k. So this is at least 1 minus epsilon times n over k. So this collection of edges form a matching, and then they all together contains at least this many edges. So they cover the at least 1 minus epsilon fraction of the edges. So because because of this computation, you might be a bit confused, but this computation is nothing much important. This just says that this is just verifying that because of this lemma on here, we know how many vertices are not touched by M. So we know this, and then we know the original number of vertices. So then that gives us the size of this. One size of this is close to maximum. Then this M prime is a collection of edges, and it should be, most of the edges should be disjoint. So if you take a maximum matching inside of there, then it's, it consists of almost all vertices in M prime. So that intuition was checked in here. And we have these 4 conditions. And then every time we apply this lemma, this 4 condition just carries over to the next graph. And then while you're doing that, we get this set M prime I. From there, we choose a matching, and then we collect them together. Then later, we get, the desired matching. So this proves the Pippinger theorem. So then now the we are left to show this lemma. So as long as we prove this lemma, we are done. And we prove this lemma using the second moment method in the next video.